Okay. Hi there, everybody. Digital Asa here, and we're going to be talking today about Chapter 4 of Physics 1110, which is motion in two dimensions. I want to start off this chapter by asking you a conceptual question. So, let's say you're a hunter in the jungle and you are hunting a spider monkey. You are going to be trying to shoot and kill this monkey, um, and it is hanging on a tree branch. The moment you fire your gun and it hears the gunshot, it's going to let go of that tree branch and fall straight down towards the ground. Okay? So the question is, where should you aim if you want to hit the monkey? At any point in that fall, where should you aim if you want your bullet to be able to hit that monkey? The moment you pull the trigger, the monkey will begin to fall off of that tree branch. So the question is, do you aim above the monkey, at the monkey, or below the monkey? And if so, how far above or how far below? Should you aim it right above, very much above, right below, almost at the ground, or should you aim it directly at the monkey? The head, the tail, the stomach. Where is it you think you should aim if you want to be able to hit the monkey? I'd like it for you uh, right now to pause the video and think for a moment and then come up with an answer that you can feel okay justifying. So think about this for a minute and wonder to yourself where you should aim if you want to be able to hit the monkey. Okay? Okay. So welcome back. The answer is actually going to be directly at the monkey. And the reason for this actually has a lot to do with gravity and how gravity itself works on falling objects. So, effectively, an object that has nothing acting on it but gravity is going to be in free fall. Free fall is, like I said, the condition where something is being pulled towards the ground only by gravity. So we're ignoring air resistance, we're ignoring tensions, we're ignoring normal forces or friction or anything like that. The only force that's acting on something in free fall is going to be gravity itself. So how gravity works is pretty simple. Basically, it is a force that pulls things that have mass together. Any object that has mass, all massive objects, uh, affect space around them. We call this a gravitational field. So basically, you got a thing that's got mass in a spot, and it is going to make this field around it that is going to pull other things that have mass toward it. So we've got this radial kind of area around it that will just cause everything else that has mass to be pulled in towards this. All objects that have mass do this. Your body does, a speck of dust does, a single proton does, but the amount of gravity you get per amount of mass is very low, which we will discuss in a lot more detail when we talk about universal gravitation and like gravity between large objects like planets. But for now, just know, basically, it takes a lot of mass to give you a measurable amount of gravity, which is why we don't consider like the gravity from an apple or something being significant. So the strength of this field is based on two things. It is based on how high the masses of the objects are and how far away they are. Let's see. So basically, here's our object with mass. I have another object with mass here. Gravity between these two is going to be stronger the higher these masses are. So both of these objects will pull each other. You'll notice that this smaller mass that I've drawn here will also have its own gravitational field pulling in toward itself. This effect will cause these two objects to get pulled towards one another. So these two objects will be attracted towards one another, and the amount they're attracted is going to be based on how big their masses are, with larger masses having stronger gravitational force acting on them. Also, the further away our objects are, the weaker gravity will get. So gravity is going to be strongest close to our massive object. Gravity is going to be weakest further away. Getting weaker and weaker and weaker the further away we go. And this should make sense. Imagine, you're on the surface of Earth or whatever, and you get into a rocket ship. The higher and higher and higher and higher and higher away you go, gravity gets weaker and weaker and weaker and weaker and weaker and weaker and weaker. At the surface, you're experiencing full gravity. The further away you get, the weaker gravity is going to get. So what this means is we can look at the radius and the mass of the Earth and determine the acceleration caused by its gravitational field. This acceleration, we're going to name that lowercase g, will affect all objects equally, no matter what their mass is. Oopsie. The reason for this is gravity gets stronger the more massive your objects are, but Also, a more massive object requires more force to move. So just how in the same way, a shopping cart full of groceries will require more pushing to actually move than a shopping cart with a single box of Captain Crunch in it. An object that has a higher mass will generate more gravitational force, but also will require more to actually move. This means that those two factors cancel one another out, and all objects will experience the same acceleration of gravity from Earth in the absence of drag. This in the absence of drag thing is really important. This means that basically if air gets caught underneath something, it can get in the way and slow that object's descent down. So for instance, like if you drop a feather and a bowling ball, the feather will take a lot longer to actually hit the ground because the drag from that air is going to be able to slow it down. So what this means is that anywhere near the surface of Earth, g lowercase g is a constant. And again, this is going to be based on the mass of the Earth and the radius of the Earth. And this comes out to about 9.8 meters per second squared. So here on Earth, if you know that an object is falling, you're able to know what rate it's accelerating at because it's going to be accelerating at little g. 9.8 meters per second squared for any falling object, no matter what, as long as we are ignoring air resistance, which we will go back and add later as we learn about some more complicated situations. But for now, if a thing is falling, we know what the acceleration on it is from gravity. It's 9.8 meters per second squared. This is a video from the BBC. It's from an old TV show that Brian Cox produced. And this clip is excellent. This clip shows this example of objects falling at the same speed in the absence of air resistance perfectly. I really like this a lot. Let's take a look at it.
7, 6, 5, 4, camera down, 2, 1, release.
So here we have a bowling ball and a feather, both being dropped inside of a vacuum chamber. All of the air has been sucked out of this vacuum chamber. So notice our sheaf of feathers is falling at exactly the same speed that the bowling ball is. With no air in the way to get caught underneath those feathers and slow them down, the rate that Earth is pulling both these objects towards the ground is exactly the same. So, I don't like this part too because all these scientists with PhDs are like really amused by something that's not necessarily super complicated, but it is cool. But anyway, the feathers and the bowling ball are going to fall at the same speed because without the air being there to slow the feathers down, the only force acting on both of these is gravity, and it will act on any mass the same. It will accelerate them the same rate. Okay, so what does this mean about our monkey and our bullet? So I said earlier that the way you want to aim is directly at the center of the monkey, and here's why. When you are doing that, the monkey and the bullet are both going to fall at the same rate. So notice in this simulation here, it does not matter what the angle or position of my gun is, and it does not matter what the muzzle velocity of my bullet is either. No matter how I orient this, as long as my gun is aiming at that monkey, because the bullet falls at the same rate that the monkey does, it will always land in the same spot. So if I'm aiming at the monkey, as it's falling, the bullet will fall at the same rate and land right where I aimed, no matter what. The angle does not matter, and the speed does not matter. So notice here I went with a really thin vertical angle. Here we're making it a little bit more reasonable, a little bit more middling rather. Here we're turning the muzzle velocity all the way up and then adjusting the angle. Check this out. Even if it's really fast, it'll still hit the monkey right in the middle. So because the bullet and the monkey both fall at the same rate, the place you want to land, to aim, is directly in the center of the monkey. Okay, so we've now established that gravity will cause all objects to accelerate towards the planet at the same rate. And for as long as we are on Earth, that rate is 9.8 meters per second square. Also, I should say this too. We call this 1g of gravity, or of acceleration. You've probably heard of g-forces before. G's is a way that we can represent acceleration, where number of g's is number of times Earth's gravity. So an object experiencing 3 g's of acceleration is experiencing triple Earth's gravity, for instance. Okay, so here I've got a list of several different objects in the solar system, and comparing their gravity together. So Earth is 9.8 meters per second squared, 32 feet per second squared. We call that 1g. The moon is about 1/6 of Earth's gravity. So you've seen footage of astronauts like jumping really high on the moon. That is why, right? Because the gravity on the moon is 1/6 the strength that it is here on Earth. So objects take a lot longer to fall back down. Mars is at 3.7. It is, less massive than Earth by a pretty substantial margin, actually. Venus is pretty similar in mass and in radius to Earth, so you'll notice that it's only a little bit smaller, 8.87. One that I think is interesting that actually surprises a lot of people is Jupiter and the Sun. Jupiter and the Sun, their gravity is a lot less on the surface than you would think. And the reason for this is because, remember, we said gravity is based on mass, and it's also based on distance. So here, let's compare gravity from Earth to gravity from Jupiter. So we're looking, remember, at the surface. Here, for instance, is Earth. This is the distance from the surface. That's going to be our distance away. Remember, gravity gets weaker the further away from the center of mass you are. So looking at Earth, we've got heavier materials, right? Dense materials. We've got rock and metal and all this water, lots of oxygen, right? So we've got a pretty decent amount of mass with a pretty low radius. Jupiter is way more massive than Earth is. It's substantially more massive than Earth is. It's the largest planet of the solar system by a lot. It's the heaviest planet of the solar system by a lot. Jupiter is very, very, very massive. It's gigantic, right? So here's the thing about Jupiter, though. Jupiter has way more mass than Earth does, but it's also a lot bigger. As a result, at the surface, gravity has to deal with this amount of space. So gravity is going to get weaker the further away from the center it is. So despite the fact that Jupiter is way more massive than Earth, it's also so big and so much less dense that its gravity is actually only 2.5 times as strong as Earth is at the surface, which is kind of interesting. Same thing with the sun as well. The sun is only 28 times the gravity of Earth, despite the fact it has over 1 million times more mass. And the reason for this, again, is because of this distance here. The further away the edge, the surface, the point in space that you're looking at is from the center of mass of that material, of that planet, rather, excuse me, the weaker gravity is going to get. So basically, the fact that they're bigger planets that are less dense means that their gravity is not as big as you would expect it to be at the surface. Now, of course, if I'm talking like right here in Jupiter, gravity is going to be insane. If I'm talking right here in Jupiter, right next to the center of mass, gravity is going to be very, very, very strong as well. So that's kind of cool. Okay, so now that we know that gravity causes all objects on the surface of a planet to accelerate at the same rate, we can look at projectiles. A projectile is any object that is somehow launched into motion by being shot, tossed, hit, kicked, whatever, however you want to get it into motion, it's fine, that follows a path directed by gravity. So projectiles, by definition, are actually in free fall. Objects that are in free fall that are following a path gravity decides. Again, we're going to treat objects like projectiles when the only source of acceleration acting on it is gravity. So something like, for instance, a rocket or a balloon has a force acting on it, right? Rockets have all that fuel exploding on the bottom that pushes the rocket upward. That is not a projectile. Something like a balloon where you fill it full of air and then you let it go and it flies around the room. All that air pressure you put in with your lungs is getting released. It's pushing that balloon forward. That is not a projectile. Okay? So things that have a force that act on them that push them or accelerate them are not projectiles. Something like a bullet is, an arrow is, a ball is. Something that's not accelerating by anything except for gravity. It's got to be in free fall to be a projectile. So, a interesting way we can think about projectiles actually is by looking at satellites. So let's say here we've got the Earth and the Moon. I want to look at the motion of the Moon as the result of a projectile path from Earth. So first things first, let's go ahead and mark in Earth's gravity. Earth's gravity is going to be a field that affects the whole space around it that points inwards. So gravity is going to point inwards towards the surface, or towards the center, excuse me, of Earth. Like this. And this makes sense, right? Here in the United States, gravity points what direction? Down. If you were to go to India, gravity points what direction? Down. South America, gravity points what direction? Down, right? It's always pointing in towards the center. So here's the moon. The moon is going to be pulled by gravity, obviously, and it's going to be pulled inwards towards Earth. But the moon has a velocity already. So I'm going to call this Fg for force of gravity. The moon has a velocity already. The moon is moving like this, in this direction. So if it's getting pulled towards the Earth, but it's already moving down, the actual path that it's going to follow is going to look like this, where it gets pulled in kind of, let me Come back just a little bit and make this a little bit better. We're going to pull it a curve. Okay, so basically, it's moving forward and it's going to fall towards the planet a little bit. Okay, so then it's here. When it's here, what direction is gravity going to point? Well, gravity is going to point in towards the center of the planet. Okay, and what direction is its velocity? Well, now it's trying to move in this direction. So it's going to fall towards the planet as it moves again, like this. And then it's here. What direction does gravity point? Well, now it points like this. What direction is its velocity moving? Well, it's moving like this. So what's going to happen? We're going to curve and fall towards the planet a little bit. Now we're here. Velocity tries to go straight. Force of gravity tries to point in. Okay, it's going to fall towards the planet again while still moving with regards to its velocity, and it's going to curve like this. Same thing, velocity like this, force of gravity pointing in like this, falling like this. So this situation where gravity is pulling in, trying to get this thing to accelerate towards the surface of the planet, because it's got this velocity on the outside, it will be able to ride the edge and curve its path down like this. And then because that force is pointing towards the center of the circle, it'll reorient it so it keeps maintaining this circular path around the edge. This is how an orbit is able to work. And this is why objects that orbit too slowly get pulled into the planet and crash, and objects that orbit too quickly end up totally escaping the projectile path and just going off into space. So this is the reason that every single planet in the solar system, for instance, has a stable orbit. In order to stay at the spot it is around the sun, it's got to maintain a very specific velocity to be able to maintain this curve pattern moving around. So we can think about a satellite like a projectile. It's curving towards the center of the gravitational field, towards the center of the planet, while maintaining this like tangential velocity as it rotates around.